So I came across this question on a rather well-known website, and nobody'd answered it since 2022, so I thought I would have a go at answering it myself. So the question says, how to find the drift diffusion components of the current density of an n-type semiconductor. And the person says, suppose we have an n-type semiconductor. The only information about the semiconductor is that the current density is constant and the quasi-Fermi level of electrons is linearly increasing in value. From this information, how to obtain, and then they want the drift diffusion components. And I guess you could do this analytically, so you could sort of set boundary conditions to your problem, and then you could sort of do some maths to get this out. But I thought it'd be rather fun if we could try and answer this using some simulation. So for this, I'm going to use the OghmaNano simulation tool. And if you click New Simulation and gallium arsenide demos, and the demo we're going to use is called a gallium arsenide doped wire. And when you double click on that and save it, you'll get up this simulation window. So here we've got a contact, and here's your semiconductor. Now you can set this semiconductor doping to what you want. I'm just going to leave it as a default here. So if we just check out what the doping is on this, so doping ions, we've got a linearly increasing or linearly decreasing number of acceptors from one side to the other, and you could change it to have donors or whatever you wanted. And if you just run the simulation, click run, it's a 2D simulation, so it took a little bit of time, and you look at the output files and you go to snapshots, and we look at and we choose, so that's the conduction band, and this little slider here enables you to step through it in voltage. So the voltage is there, you change the voltage, and basically you can watch the conduction band change as the simulation ran. But what we can do is we can go to J of n, which is the total current density as a function of voltage, but there's also two files called J of n diffusion, and it plots it on a log scale, so sometimes this page just got the L button and it gets back. Diffusion, and there's also one called drift that you can sort of play with. So those are the two components, the drift and diffusion components. It's actually quite hard to separate them when you're trying to calculate it numerically, because the current is a very strong function of position and voltage. So you can't, it's quite hard. You can't really just sort of take the derivatives and plot the current. You've got to do it in sort of a bit of a special way that this software does. So, and that's obviously in 2D. So you can play with it. That's it really. So I think that answers that question, or at least gives some idea about it. And I guess I'll just say finally, if you want to sort of change the parameters and change the values or whatever of the materials, you could do it by clicking this button and going into the setting the material parameters. So you've got like mobility and recombination constants and stuff like that. So I hope that was interesting. So thank you very much for listening.